All right, let's put it all together, everything we've learned so far this semester as a quick wrap up. So at the beginning of class, we spent a lot of time kind of on the theoretical concepts. We learned about expected value, variance, covariance, and matrix rules. And this helped us be able to derive least squares estimation, which was kind of the main focus of this class, where we've got some outcome, y, we have some predictors, x, and we're trying to come up with coefficients that describe the relationship between x and y. And then we covered things like law of total expectation and law of total variance. And that allowed us to do things like get the expected values. And so we were interested in getting the expected value of beta hat, so our estimate for beta, which used the law of total expectation. And then we were interested in calculating the variance and covariance of beta hat. And to do that, we used the law of total variance. Then we learned about bias. And so bias is just the expectation of, in the case for beta, the bias would be the expectation of beta hat minus beta. And we showed that that was equal to 0. And that's building up to showing that least squares is an unbiased estimator. And we also talked about minimum variance. And so we also, in deriving the least squares variance estimator for beta hat, we were able to also show that that was the smallest variance of any linear unbiased estimator. And so this basically culminated in blue, which is that least squares estimation is the best linear unbiased estimator. And so what we were doing here at the beginning of class was sort of justifying why we were going to spend the rest of the class focusing on least squares and how each of those components were actually derived mathematically. And so we used that bias and that minimum variance there to justify that blue. And then we talked about the residual sum of squares, which is equal to just the sum of the residuals squared. And to do that, we needed to use some matrix rules. We learned about the trace. We learned what it meant to be idempotent. And that let us take the expectation of those residual sum of squares. And we were able to plug in some rules that we had learned about expected value for that. And then we also were able to estimate sigma hat squared, so the model variance. And for that, we used some rules about the variance and covariance that we learned at the beginning. And we actually plugged in the variance of beta hat for that as well. Or plugged that in rather to the variance of beta hat. That was an important component there, the sigma hat squared. And then we learned about f-tests, and so when we were trying to compare different models, we learned about how we could do that with something known as an f-test. And these f-tests used the residual sum of squares that we had learned about. They also used that sigma hat squared that we had just estimated. And finally, we got to hypothesis testing, and so we were able to do hypothesis testing with these f-tests and also with confidence intervals. And so we were able to derive how you could calculate a confidence interval for beta hat using that variance estimator that we had estimated previously. The square root of that is the standard error, and how this is t distributed, and so we could use the t statistic to be able to help us get at this hypothesis testing, and also to be able to use that t star value to be able to estimate the confidence interval itself. And so this kind of covers the theory that builds up to kind of why least squares is sensible, because it's the best linear unbiased estimator if the assumptions hold. And also kind of how to actually derive each of these components. You did it by hand, you did it in R, and then you did it kind of using functions that R provides for you. So that was the beginning of class, and we sort of were doing that just to build up some intuition and also to kind of get our statistical chops going there to get ready for the next half of class. And so then we started talking about interpretations, and we spent a lot of time on confidence interval interpretations in particular. You've simulated confidence intervals to be able to demonstrate that when we're getting a confidence interval for something like a beta coefficient, so when we're getting a confidence interval for something that is fixed but unknown, when we're interpreting it, we need to interpret it very carefully. And so the interpretation there would be if we were to repeat this process many, many times, we would expect that 95% of the confidence intervals calculated would and would contain the truth there. And so we talked a lot about kind of how this was a comment on the procedure rather than on the individual confidence interval itself, how the individual confidence interval was not a probabilistic statement because the truth is fixed, and so we can't talk about a single confidence interval having a certain probability, but rather we talk about kind of the collection of confidence intervals, the probability that all of those confidence intervals are the proportion of those that would contain the truth is what the confidence interval actually is telling us. And then we talked about assumptions, and so the first half of class really was assuming certain things about our setting in terms of our data and our error distributions. And given those assumptions, all the different pieces that we derived held true. But then we learned kind of how to test whether those assumptions really are valid and what to do when they're not. And so the main assumptions we focused on were linearity, constant variance, normality of the errors, and that the errors were independent, so whether they were correlated or not. And so we can test these. The linearity, we could look at a residuals versus fits plot, and same with constant variance. For normality, we looked at QQ plots and histograms. And for correlated errors, to understand whether the errors were independent, we were able to look at the structure of the data. And so for that, you needed a little bit of extra information. Often, there wasn't really a single test that you could do for correlated errors. You had to sort of take into account what you knew about how the data was collected, whether it was collected over time or over space or something like that you needed to account for. And then we talked about kind of once we've determined whether or not these assumptions are met, when they weren't met, we talked about how we could actually fix it. And so for linearity, we talked about transformations. We did a little bit with polynomial terms to be able to include those in the model. For constant variance, we talked about weighted least squares and generalized least squares. If constant variance is the only problem, then weighted least squares solves that problem for us. But if we also have the issue of not having independent errors, then we need to switch to generalized least squares. Normality, when normality is a problem, we can use robust regression to help us with that, especially in the case of outliers. And then when we have violated the independence assumption, when we have correlated errors, we talked about how we could use generalized least squares to be able to account for that. And then we also talked about unusual observations, things like leverage points, outliers, influential points, what the difference is between each of those and what to do in the presence of them. And in particular, we focused a bit in the recent labs on when you have outliers, how you could do something like robust regression, for example. And you would want to maybe assess whether or not your answer for robust regression got a substantially different answer than you got when you just ran a normal least squares regression. And if you see a big difference, then perhaps robust regression is a better way to go. And the other thing to note with unusual observations is that sometimes you might have an observation that's unusual, and all that's important to do is to note it. So when you're describing your data, you note, we have this observation that is unusual, but we think it's valid because of XYZ, or we don't think it's valid because of XYZ. And then most recently, we've covered creating reports in R Markdown. We talked about code chunk options, making pretty tables, using inline code, output formats like PDF, Word documents, and HTML documents, and then culminating in a final plot. So we've spent a whole semester talking just about kind of linear regression methods, but we've really dived deep into them. And it's culminated in sort of once you've fit your linear regression model, you feel comfortable with those estimates that you've calculated, how you can actually communicate those. And a forest plot is a really good way to do that because it allows you to show both the estimate and the confidence interval. And you can always incorporate things like if you want to draw the audience's attention to certain points, you could color them. For example, here I've colored them by the significance of the p-value. And you could annotate points, and we talked about how to do that as well.